All right, chemistry SOL people. On this video, we're going to go through the practice items on the online Test Nav Practice SOL for chemistry, and just go through it question by question. If the video takes a little too long, then it might be two parts. So this will be, the first few questions. If we make it through all 27, then there won't be another video. But if we do, if it takes a little too long, then we might cut this one in half and do another video. All right, so let's jump into it. So another thing to know is as we go through it, this this is my answer key to the practice items. And so you might want to have this open as we're going through the video, or print this out so you can see kind of the notes that I have for each question. I'm going to explain it verbally, but if you want to see it in writing, you might want to reference this thing, and it's posted in the same folder. All right, so that is available to you. All right. So again, if you want to take it, the practice test yourself, you want to click on Test Nav, and again, it just takes a little bit of time to boot up, so let's do that. All right. Again, don't log in. Just go to Virginia Practice Items. And we'll go to Science, Chemistry, Non-Audio, Start. We have to agree. And start. All right. So let's go question one. All right. So the table shows the experimental determined density values for this compound. What is the percent error if the actual density is this? So this is what our true value is, and what we need to do with that data is get an average, and that'll be our experimental data. So we're going to add these up: 1.87 plus 1.94 plus 1.92. We're going to divide by 3, and the average comes out to be 1.91. So then all we have to do to calculate the percent error is do the absolute value of the difference. So we'll do 2.02 minus the average, which was 1.91, and then we'll divide by the true value, which is 2.02. So we'll do the difference of the two values, and then we'll divide by 2.02 times 100, and you should get 5.4%. All right, moving on. All right, so here, experimentally determined data for BE3N2 says how many significant figures will result when calculating the density from this data. Okay, so remember, density is mass over volume. We have a mass and we have a volume. They also gave us the molar mass. So here's something to understand. They might give you some information you don't need. So we don't need the molar mass here, okay? And we're not going to actually calculate the density. We just need to know how many significant figures our density should have. So we're taking this number, mass, dividing by this number, volume, and we're going to get grams per milliliter. But what we have to recognize is this has 4 significant digits, our mass measurement does, but our volume measurement only has 3. And when we multiply or divide, what limits us is the least number of sig figs we're using. So this number only has 3, so our answer has to be limited to 3. So the answer is 3 there. Okay, and again, that molar mass is just kind of a distractor there. We didn't need to know it to answer this question. All right, moving on. All right, so we have our first kind of technology enhanced question. So we're going to type our answer in here. Let's read our instructions. Okay, calculate the atomic mass of the theoretical element using the data in the table. Your answer must be rounded to the nearest tenth. So we're going to go to 1 decimal place here when we're all done. All right, so to calculate average atomic mass or atomic mass, we do the mass number of the isotope and we multiply it by its percent abundance, and we do it for each one. So I'm going to do 10 times 0.92, I'm going to do 11 times 0.065, and 13 times 0.015. And then all I have to do is add those up, okay? Now the other way to do it is you could do 10 times 92, 11 plus 11 times 6.5 plus 11 times 1.5, or 13, sorry, let me redo it. You could do 10 times 92 plus 11 times 6.5 plus 13 times 1.5, but then you would have to divide everything by 100. So you can either move the decimal place to the left twice for each of these and then multiply and add them all up, or divide by 100 at the end. Okay, either way is fine. But if you do it right, you should get 10.1. Now, we didn't need to include units, but the units would be atomic mass units, AMUs, just in case that does come up on your actual SOL. All right, so let's move on. All right, so this gives us protons, neutrons, and electrons data for sulfur atoms. Now remember, the one thing atoms of the same element have to have in common is they have to have the same number of protons. So notice all these atoms have 16 protons, that's the atomic number. And if they're neutral, they would have the same number of electrons, so they all have 16 electrons. So what's different about isotopes is their number of neutrons. So boom, we know our answer there would be A. Different isotopes of sulfur have different number of neutrons. That's what the data is showing us. We don't even need to know this table to know what isotopes are. We should be able to define isotope as atoms of the same element with different masses, or another way to say that, the only way you can have a different mass but be the same element is if you have a different number of neutrons. So you could say atoms of the same element with a different number of neutrons. Okay, so that's, again, this answer here. All right, let's keep on rolling. Okay, also notice here that they said sulfur parentheses S. So if I wanted to look at my periodic table, I know I'm looking up that one to figure out sulfur, all right? But really no need to do that because they gave you the atomic number right here, okay? All right, so let's look at this. So which element has atoms that most likely have the greatest shielding effect? Okay, so shielding effect is one of those periodic trends you want to know about. And what you need to know about shielding effect is that it increases going down, but stays relatively the same going across left to right. So really, the greatest shielding is going to be which one of these elements is furthest down on the periodic table. So let's pull up our periodic table, okay? And what we'll notice, hopefully you notice this, we got strontium, calcium, magnesium, barium. They're all in the second group, magnesium, calcium, strontium, barium. And the one that's furthest down is barium. So barium would have the greatest shielding. Okay, now what shielding is core electrons, so the non-valence electrons shield, repel the valence electrons from the nucleus. And so the more core electrons you have, the greater the shielding. And as you go down, you gain another energy level. And that means, you know, as I go from here to here, once were my valence electrons, as I go down to this energy level, are now my core electrons. So as you go down, you get more core electrons, you get more shielding. Okay, moving on. All right, so here it says, drag each electron spin arrow into the appropriate box. You must place all spins in correct order. Each arrow may be used more than once. And we want to do the orbital notation, the orbital filling diagram for silicon. They gave us the chemical symbol. We'll come over here. We'll find silicon on our periodic table. It's here. And we need to write the orbital diagram, okay? Now, remember, orbital diagram and electron configuration are basically the same thing. So the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p2. Okay, so we're going to finish with 3p2. And what we need to understand is, so this is one orbital, this is one orbital, this is one orbital, this is one orbital. We got 3 orbitals. And remember our rules. In order to be in the same orbital, electrons must have opposite spins, so I can't have up, up, or down, down. Okay, so I know 1s2, 2s2. Okay, now we're going to go 2p6. So we're going to go 1, 2, 3, 4, 5, 6. Now, you didn't have to do it that way, but you probably want to because it's going to matter when we get to 3p. So up, 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 then down, down, down. So then we're going to go up, down for 3s2. And then we got to finish off with 3p2. So only 2 arrows. But remember, in the same sublevel, you're going to go different orbitals. Okay, different orbitals first. but with the same spin. So you're going to go up, up. You're not going to go up, down. You're not going to, right? This would be incorrect. That would be a violation of Hud's rule. So we're going to go up, up. Now, technically, you should be able to do that, but let's just be safe and always just go from left to right and always start with an up arrow. Okay, so that would be the orbital notation for silicon. All right, so moving on. All right, so we're doing another electron configuration, but this is the actual electron configuration and just not the orbital diagram. So for argon, so let's find argon. Argon is one of our noble gases. It's here. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and that's where we'll stop. So notice this 4s2, we're not going to put anything in there. Notice it does say some boxes may be empty. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, and we're done. Okay. Right. So here it's saying, what's the oxidation number for a fluoride ion? So if you haven't seen that term or heard that term, oxidation number, anytime you see it, just think charge. So it's just asking you what's the charge of a fluoride ion, and notice it has to, you have to do plus or minus for whatever charge it is. So hopefully we know that fluoride is -1, but let's remember it's in this group, and so it needs to gain 1 electron to get to that noble gas configuration. So if it only has to gain 1 electron, it'll be -1. All right, so remember, +1, +2, +3. And then when we go to nitrogen's group, -3, -2, -1 for the halogens. All right, so we'll go here, -1, and we're good to go. All right, so here's kind of a funky diagram. Maybe you remember looking at something like this with your teacher when we did electron configurations. I'm going to show you a shortcut on how to do this. But what you would do is you have to remember that every S sublevel can fit 2 electrons. Every P sublevel can fit 6 electrons. Every D sublevel can fit 10 electrons. Now, another thing we want to understand for this reaction is, I don't really like the wording of this, but it's just the way it is. It says, how many electrons can you completely fill the orbitals from 1s to 4p? And let's understand that it's not stopping at 4p, it's including 4p. So we're going from 1s all the way through and including the 4p sublevel. So again, 2 for the S, 6 for the P, 10 for the D. And just follow the arrow, okay? So 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6, and we would stop there. So we would add all those up. So again, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6. So if you were following along there, that math is 36. Now, easier thing to do, I think, is if you know the blocks of the periodic table, S block, P block, D block, F block. Instead of using this, just go to your periodic table and notice, again, it says 4P, so find 4P. So row 4, sublevel P, and go to the end of that block, 36 electrons. Each space on the periodic table counts as a proton, but it also counts as an electron. So we're going from here, 1s, all the way to the end of 4p. It's going to be 36 spaces, so that means 36 electrons. So if this had said 1s through 3d, remember row 4, but when we get to the D block, this is 3d. So if we go to the end of 3d, 30 electrons. If it had said 1s all the way to 3s, find row 3, sublevel S, go to the end, 12 electrons. Okay, so you can use this chart, perfectly fine, but I think it's easier if you really understand the blocks of the periodic table. That's the way you could get there a little bit quicker, okay? But again, it's not about speed. You have as much time as you need, all right? All right, so this one, we gotta be careful, all right? We gotta be really careful. So scandium, if we're finding the electron configuration for just scandium, let's ignore, let's say they didn't say anything about scandium in this compound. If we were looking for neutral scandium, it would end in we do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we would stop at 3d1. All right. So this isn't the right answer for this question, but if they had just asked for scandium, this is the correct electron configuration for scandium. Remember, when you get to the D sublevel, you have to subtract 1 from the row you're in. So it's 4s, but then it's 3d, right? Okay. But let's understand what this means here. Okay, when scandium's in a compound, scandium's a metal. When a metal's in a compound, it's a cation. So this isn't neutral scandium. This is scandium 3+. And let's understand, 3+ means it lost 3 electrons. So it's not going to have the same electron configuration as neutral scandium because it doesn't have as many electrons as neutral scandium. All right. So if this is my normal electron configuration for scandium, these last 3 electrons, the 2 here and the 1 here, are going to be removed because we're talking about scandium 3+. And so this is the actual configuration. Another way to think about it is if you lose 3 electrons, if you can look at this and know that that's scandium 3+, move back 3 spaces. 1, 2, 3. So it's really just, hey, what's the electron configuration for argon? Scandium 3+ has the same electron configuration for argon. Now, let's move forward. Let's think about the SOL in total. They're probably not going to ask this specific question because it's a practice item. But anytime they ask you for an electron configuration of an element, but the element's in a compound, all right, all you have to do is find that element on the periodic table, go to its closest noble gas, and write the electron configuration for that noble gas. So if they said like bromine, but it was in a compound, I wouldn't write the configuration for bromine. I would write the configuration for krypton. If it asked for, sodium, but it was sodium in sodium chloride, I wouldn't do neutral sodium. I would go back 1 space, and do neon. Okay? All right, so moving on. All right, so we got to know our diatomic elements. Our diatomic elements are hydrogen. So if we go to our periodic table, hydrogen's a diatomic, then nitrogen, oxygen, fluorine, chlorine, bromine, iodine. I like to say there's 7 of them, so go to number 7 and make a 7. But then you have to also remember hydrogen, okay? But this is just asking you which of these groups, so which of these vertical columns has all their elements are diatomic, and that would be the halogen group. So that one right there, okay? So just keep going. All right. So here we're asked to name the lead oxide. Okay. We're asked to name this compound. Okay. So a couple things we have to know. It's ionic. All right. Can I use that? No. Yeah. No. Okay. It's ionic. So that means, remember, ionic compounds don't use prefixes. So you're not going to be using this thing because it has di in front of it. You're not going to be using this thing. It has tetra. You're not going to be using this because it has di again, and again you wouldn't be using this because it has tetra. Ionic, no prefixes. So that only leaves oxide, lead 2, lead 4, and oxygen. So we have we've narrowed it down a little bit. So remember, oxygen is the second thing in the thing, so it's going to be the last part of the name. So it's going to end in oxide. Okay, so we know it's going to be oxide, not oxygen. Okay, and then it's just a question: is it lead 2 or is it lead 4? All right, so we got to figure out the right Roman numeral. Lead is one of those elements that needs a Roman numeral in the name, so we got to figure out. So if you guessed lead 4, you'd be right. Now the reason that is because if we remember, oxygen O is a -2 ion, right? It needs to gain 2 electrons. So in this compound, O is -2, but notice that you have 2 of them. So that total is -4. So that means the 1 lead ion has to be +4 to balance out the charge. And so that's why it's lead 4 and not lead 2. Okay? All right, let's keep on rolling. All right, so here we're gonna drag and drop our coefficients to balance this equation, but notice what it says, each box must have a coefficient. That means One is not understood in this question. So if you think you have a one, okay, you need to put one and don't just leave it blank. That's what those instructions are telling you, okay? So what we're gonna do is I have one aluminum, two aluminums, so I'll put a two here, okay? Two irons, one iron, I'll come over here and put a two. Three oxygens, so everything's balanced, but I need to make sure I put my ones where they need to be. All right, there you go. So if you had left those blank, you know, if you're taking my test, I'd give you full credit because one's understood. However, not in this question. It's not. So it would be marked wrong if you didn't put those ones there. So watch out for that. Make sure you read your instructions. Okay. All right, let's go to this one. All right, what is the molecular formula for a compound with a molar mass of 92 and an empirical formula of NO2? So what we're going to do, we could process of elimination a little bit. So the formula that we pick has to reduce back to this formula, right? So we could go, that doesn't have the same ratio, and that doesn't have the same ratio. So I know it can't be A or C because those don't reduce back to this ratio, 1-to-2 ratio between nitrogen and oxygen. So it's either B or D. So what we could do is just, if we add these up and we add these up, whatever has a molar mass of 92 is our right answer. So that's one way to go. Or the other way to go is to find the molar mass of this, of the empirical formula. So if you go to your periodic table, one nitrogen is 14, and two oxygens would be 32, 16 plus 16. So the mass of this is 46. And so if you do 92, the molar mass of the compound, divided by the molar mass of the empirical formula, 46, you're going to get a whole number. So 92 divided by 46 is 2. So it is just telling me to double this compound. So if I double the subscripts here, I'm going to get that compound. But again, if you add it up, 14 plus 14 plus 16 plus 16 plus 16 plus 16, you're going to get 92. So that's the right one. All right. All right. So let's talk this one, equilibrium. You probably haven't talked a lot of equilibrium in chemistry class, whether you're taking honors or regular. We just haven't gotten to equilibrium. So what you need to understand is a catalyst doesn't affect equilibrium, but everything else listed here does affect equilibrium. So you have to select all the right ones, and all the right ones are everything there except for a catalyst. All right. Okay. So we're gonna stop there. That'll be part 1, and I'm gonna come back and finish 16 through 27 in another video. Okay.